Zhu. I'm a computer engineer.
I'm also, I'm a computer engineer.
All right, very good. We have our three judges with us today, Joe, Clark, and Stewart. We're going to have 12 minutes for your presentation, and then after that, we'll have 2 minutes for questions and answers.
Thank you.
Okay, go ahead, proceed.
Hello everyone, we are Banshee Uav. I am the EC Robotics Lead Maggie.
I'm Alex O, the robotics sub-team lead.
And I'm Winston Zhu, the robotics deputy.
So one major issue with commercial UAVs, such as the one seen in figure 2.1, is limited flight duration. This becomes an increasingly bigger problem in military applications where they use these UAVs to scout out the battlefield and collect critical life-saving information. Typically, these UAVs with no payload or normal speed can last for about an hour of flight. However, as we increase the electrical power consumption by increasing the speed or by adding more weight like sensors or cameras to increase the accuracy of the readings, the flight time drastically decreases. So to enable these long endurance flight missions, we have created a replicable ground system that will allow us to autonomously and safely swap the batteries out for new ones and collect that critical flight mission data and send it to a very secure server. Additionally, it can be placed in remote, off-the-grid locations, allowing us to operate this system in almost anywhere.
So here is our robotic ground system design. It is comprised of 3 parts. First, the ground control station, which is a safe place for the drone to land on. Next, we have the battery vending machine, which is an 8-chamber storage system that keeps the battery charged at all times. Lastly, we have the battery transfer pod, which is a robotic arm that takes the battery from one station to the other. Now, how does it work? So, as you can see, the drone lands onto the ground station, and the robotic arm pulls this battery out of the drone. It then brings it to the battery vending machine, where it is placed into an empty chamber, and the battery vending machine will then rotate accordingly and dispense a new fully charged battery. The robotic arm will then grab that battery and bring it back to the drone, where it is placed into the chamber, as you can see here, and then the drone is ready to take off. We estimated this turnover time from the time the drone lands to the time the drone takes off to be around 5 minutes or so, which is really efficient because one singular LiPo battery actually takes 1 or 2 hours to charge up.
So this diagram represents our hypothetical long endurance flight mission. For example, if we want our drone to get from Los Angeles to New York, this is possible to do with 1 battery life. But by placing our system all across the United States, the drone is able to make multiple stops at these stations to exchange its battery and continue on its journey rather than staying at one place to charge its battery. So if you see in our first slide, we have the Storm 4 quadcopters we use for testing. Since our system is modular, we are able to support other types of drones. Our first drone is the Baby Shark, which is a commercial electric vertical takeoff and landing UAV provided by the Air Force Research Lab. Our second drone is the Synstro UAV, which is a student designed drone and catch a lot of people.
So here's the first component of the ground system, which is the ground control station. It is a large 7x7 AR marker that the drone's computer vision will scan and land autonomously onto. Additionally, the ground control station will also realize the drone's presence by the induction coils that we have. The induction coil also play a really critical role as it enables hot swap, meaning that when the drone's battery is completely removed from the drone, all the onboarding electronics will still be kept on due to the induction coil. Without it, all the flight mission data and the flight computer will be erased, since it is a volatile system.
Additionally, when the drone lands and the induction coils connect, 2 other processes enact, which is the data transfer from the drone to our virtual private server, transferring all the mission data and flight information, which will eventually be sent to our web app. And it will engage the locking mechanism, which is controlled by this custom-built wonder-driver PCB seen in figure 8.3. It engages these locking mechanisms, which are controlled by these differential gear systems. And the reason why we need the locking mechanism is to hold the drone in place to allow for safe and reliable switching of the battery by the battery transfer pod to prevent any shifting or any winds from blowing the drone out of place and then causing a mishap.
So here is the second component of the ground system. It is the battery vending machine. As you can see in figures 9.1, it is a circular rotating system that can store up to 8 chambers. In the center, we have a NEMA 23 stepper motor that can accurately rotate the batteries to its very specific location. In the center, we have figures 9.2, which is the copper contacts that we have designed that allow easy connecting and disconnecting between the system and the battery. Lastly, we have AR markers that are on the battery chambers itself, so that when the camera on the robotic arm scans it, it should be able to display multiple parameters. In the back of the chamber, which is over here, this is the battery chamber. In the back of the chamber, in this square box, rectangular area right here, we have all the circuits. The first circuit we have is the wireless battery management system, which will capture and send the voltages of all the 4 S-LiPo battery individual cells to our web app. Secondly, we have the LiPo charger circuit, which will charge the battery to its specific percentage. And lastly, when we put all of these circuits together, we have compressed a PCB board that will be stored in the back. See, as you can see, all these circuits are fairly large, so by compacting it onto a PCB, we can store it in the back. Currently, this PCB is being fabricated as we speak. Here is the web app designed by our students. If you check out this website, you should be able to see all of our battery data as well as our flight data from the ground control station and the battery vending machine. Unfortunately, at this time, we are currently trying to switch this website to be compatible for the phone, but it is best used on the desktop.
This is the third component of the system, the battery transfer pod. You can also be seen in front of you right there. So it's comprised of many different elements, such as the depth sensing camera, which allows us to see the AR markers on the battery and grab its positional data, allowing the robotic arm to grab it. The robotic arm we're using is the Open Manipulator X, which is an open source 5-degree of freedom robotic arm provided to us by Roboticists. Additionally, we have 2 onboard ultrasonic sensors, which allow us to position it between the ground control station and the battery vending machine appropriately. It also utilizes an induction coil as a wireless charger for our onboard LiPo battery to prevent any wires from entangling while it's traversing. Because if we did not have this wireless charging unit, we'd have to constantly connect a wire, and then it might cause issues while it's traversing through the track if it disconnects. So this is some real footage of the battery transfer pod in action. Figure 12.1, you can see the battery being extracted from the drone. And in figure 12.2, you can see the integration between the battery vending machine and the battery transfer pod, where the battery vending machine rotates a battery into place, the battery transfer pod then grabs the battery and then places it back into the battery vending machine. And then in figure 12.3, we can see the battery transfer pod grabbing the battery, traversing along the rail as if it was grabbing the battery from the battery vending machine and then placing it onto the ground control station where the drone would be.
So now you know the parts of our system, how we power it. Since our system is placed in rural areas, we cannot just plug the system into an outlet like we did in our lab. So in this case, we'll use 190 watt solar panels, which provide around 540 watts of stable power to our system. We'll also include a 48 volt LiPo battery, which will power the system at nighttime or times when there's no daylight. Since our system deals with high voltage and high amperage, we'll use a DIN rail to protect our circuits from over voltage or short circuit. We'll also distribute the power equally from the solar panels to the three subsystems.
So, you have seen all 3 of our systems. Individually, they are very complex, but put together and integrated together, we have created a system that enhances the flight time for many UAV drones. As a reminder, our turnaround time takes around 5 minutes only, which is really efficient because one singular LiPo battery takes 1 to 2 hours to charge up. The application of our work is that everything here is autonomous. From the time the drone lands, to the robotic arm and the rotating battery vending machine, everything is autonomous, meaning that we have less human errors as well as human interaction for our own safety. Our system is very eco-friendly. We do use solar power and solar energy, and also this whole prototype took us around $1,500, meaning that if we were to mass produce this, it would be very efficient to be placed around the US. Lastly, we would like to acknowledge all of our sponsors as well as our faculty advisors for helping Banshee become Banshee now.
Thank you.
All right, very good. I applaud you. You were 2 minutes under, and you presented an amazingly complex amount of information. So let's, with that, we have a couple of minutes for our judges to ask questions.
So what's the most challenging, technically challenging portion of your project?
In my opinion, the most technical part was integration. Everything works really well by itself, and I can show you an example of the difficulties we had. As you can see, right here, or I don't know if you can see, but every chamber has an open slot. Before, if you looked at the way we designed our battery vending machine, each component had no slots. So this was before integration. This is before we had to deal with the robotic arm and the motion of the robotic arm. So integration, in my opinion, was the most technically difficult part, because each part, if it doesn't go incorrectly, then it affects the other components as well. So this was an example of one design aspect that we had to change.
I would agree with that answer. Integration was definitely the hardest, or the most technically challenging thing about this project. Not only am I in charge of the battery transfer pod, where I have to integrate with the ground control station and the drone, I also have to integrate with the battery vending machine, where if all these three elements don't line up properly, the entire system would break. Additionally, robotics is a subset of Banshee Uav as a whole. So there's an entire aero department. As you can see, we support up to 3 drones. And so being able to adapt those drones to our system is really challenging, but very rewarding.
So the challenge I faced was creating the transfer pod. So since most of the transfer pod is CADed, we had to pre-model all of the parts. But since each 3D printer is not really always 100% correct, we have to account for the misprinting or the tolerance between them. So every time we print a certain product out, we have to test it, and if it doesn't work, you're gonna have to either use a different printer or refix your model. So that took a lot of time to just building the whole transfer pod.
Going back to what he said, basically everything you see here is kind of 3D printed with our own printers, like personal printers. So yeah, it took a lot of time to print all of these stuff. Yeah.
First, I want to compliment you on your presentation. It was very well organized. You all spoke very loudly and clearly. It was very easy to understand. Fascinating technology. I can see this working very well in a clean environment, but in a rural location where you have insects and birds and that sort of thing, if there might be some challenges, maybe there has to be some type of shelter that the drones fly into or something. But just again, wanted to compliment you on a very good presentation.
Thank you.
Thank you.
To add on to what you said, we actually have a systems team that is currently finding a way to, like you said, avoid any of those obstacles. So what we kind of have in mind is that a camera where we can see our whole area, as well as a casing like you explained with the box. So yes, we do have that in mind, because we do want to send this out and practice it in not the lab area, but outside.
Yeah. Do you have an application for Tesla batteries?
Application for Tesla.
Where you drive your Tesla in and it just
That is my what's it called, elevator speech when I tell this project. Because people, I guess most people use cars rather than drones, so I use the Tesla as a battery swapping, because you have to wait an hour for a supercharger, right? So it's the same application, but for drones.
So feedback I give you guys.
Oh, sorry, Stu, were you?
Yeah, I'm good.
Feedback I give you guys. As Stuart said, great presentation. You were very clear and easy to understand. 2 things. One is that I don't know, maybe just me, but it seems like this technology, what you guys did, what you developed, is already out there in the market. It's just, I don't know if it is or isn't, but it just seemed to me like I've seen this before somewhere. And if it is, then I'm saying to myself, well, then is this really new technology you're Maybe it's the way you guys did it, maybe it's the way that you guys went about doing it, maybe it's that you improved something, but I guess, what I'm getting to is that I'm not sure that I see the technological advancement that was made by this particular project, that's one. Number two, Maggie, you and I know each other quite well, so I'm gonna direct this comment to you.
Yes.
What I'm gonna say is, when you're making a comparison about things, for example, 5 minutes to change out the battery, 1 hour to charge the battery, and then using that as an efficiency enhancement, that's not apples to apples, that's apples to oranges, okay? Apples to apples would be 5 minutes to change out the battery, and it normally takes 10 minutes to change out a battery on another system. That would be apples to apples. Apples to oranges is 1 hour to charge, 5 minutes to change out. You're not talking the same thing. So just think about that as you go forward in your presentation. Anybody want to offer any comments back on that first question that I asked? Is this new technology?
Actually, so MIT did do a battery transferring. However, they didn't do a circular motion, and there was no robotic arm. So I guess there is a design with battery, like vending machine type of thing. But it's a vertical, they had a vertical one, but we decided to do a circular one. And actually with drones, I don't think they have this for like a system like this. Because I know like NIO, I don't know if everyone knows NIO, it's a car company in China, EV company, and they actually did this, but for cars. So I'm not too sure if they have any for drones. But yeah, I know for MIT they did have a vertical one, but we moved it to the circular one and with the robotic arm with the pod.
I'd also like to add on to that. The system is a modular system, allowing it to be expanded to a much larger length. Because one issue with like drones in general, or safety-wise, is if these batteries are way too close, or the battery vending machine is way too close to the drone or the landing station, and there is a mishap that happens, that will cause a huge environmental impact, causing like a huge fire, possibly a forest fire, or something of that nature.
Thank you, fellas.
All right, any other questions? All right, thank you very much. Okay, we are done with the first portion of our session. And so appreciate everyone's participation. Judges, appreciate your time. We are done with session 4.